Welcome everybody to RISE Learning Machines seminars. Today we'll dive into imitation learning and reinforcement learning. RISE is Sweden's research institute with nearly 3,000 people working around 35 different locations on a vast array of different topics. At the computer science department, we work on AI projects for the benefit of society, and we organize these weekly learning machines seminars. We also record these. So if anyone of you wants to be removed from this recording, just let us know afterwards. There are also a number of really great talks recorded on our YouTube channel, so please check that out. Today's speaker is Alexander Ilin, who is professor of practice at Aalto University in Helsinki in Finland. He obtained his PhD from Helsinki University of Technology under the supervision of Erkki Oja and Harri Valpola, and he contributed a lot of work to the body of work on independent component analysis and principal component analysis. He has been working on Curious AI and Amazon and Analyze 2, and he's currently teaching the vastly popular deep learning course at Aalto University with more than 400 students at the moment. So today's topic is hierarchical imitation learning with vector-quantized models. And with that said, I'll hand over to you, Alexander.
Thank you, Olaf. Thank you for the introduction and thank you for the invitation. Let me share my screen. Okay, I guess you can see my screen, right?
Yes.
Okay. Good. Yes, so today's talk is going to be about hierarchical imitation learning, and this is a joint work with Kalle Kuenpää, who is a doctoral student in the Department of Computer Science, and Joni Pairinen, who is a professor at Aalto University. Okay, so I wanted to have a slide about my research and my research interests. So my mission, what I want to build, I want to build powerful predictive models of the world, and I want to use those learned models for planning future actions in order to, behave intelligently in order to solve complex tasks. So one line of my research is focused on deep unsupervised representation learning, because as Olaf mentioned, like I have a history of doing research in unsupervised learning. And nowadays we focus on learning so-called object-centric representations, which means that we want to understand sensory inputs in terms of objects that somehow interact with each other. So we want to understand what objects are, and we want to extract those objects in unsupervised way. So we don't have any supervision on what those objects could be. Another line of research is related to building neural networks or like data-driven models for modeling physical processes. And I think this is especially important for many Finnish industries, because in many industries there is not much data. So the data scarcity is a big problem. And if you want to build powerful data-driven models to model physical processes, then of course there is a danger of overfitting. So in order to build powerful models from little data, we need to use the knowledge of physics. For example, we may know that some processes that we model, they conserve energy, and we can use that knowledge and incorporate that knowledge in building our neural network. But then I want to use those models that we learn, the models of the environment, in order to do planning, to plan like future actions for an intelligent agent. So some line of research is focused on improved planning and model-based reinforcement learning, and this talk is going to be about this topic. But what I also find very fascinating and interesting in the future is connecting this world model building with language, for example, using large language models so that we can use the knowledge that is that is encoded into large language models, such that when we learn world models, we can kind of use that knowledge that is encoded, and our reinforcement learning would be able to learn to behave in new situations in a kind of much faster by using the knowledge from those large language models. I also have a bunch of collaborations with companies, for example, Fingrid, Neste, Typo, or Nokia, Bell Labs, F-Secure, and also some real-world reinforcement learning projects. So I want to have just a couple of slides about my collaborations on applied reinforcement learning. So a couple of interesting projects. In one project, we collaborated in F-Secure. It's a company that does works in the cybersecurity business. And in that project, we wanted to build a machine learning system for detecting attacks. But someone cannot see the screen. So is the screen visible?
Yes, it is visible.
Okay.
So I think you can go on. We'll try to figure it out here.
Yeah. So, but the problem is that if we want to build a machine learning system, that we need to actually have data. And the problem in that domain is that, again, there is quite little data, and collecting that data about attacks is expensive and difficult. So in that project, our idea was that we use reinforcement learning to collect data about attacks. So basically, we train our agent to perform attacks, and in particular, we use reinforcement learning to perform privilege escalation in Windows 7, and we show that it's possible. And I believe in the future, attacks will become more and more automated, and understanding what are the limitations of the current reinforcement learning in this domain, and how reinforcement learning can be used in this domain is very important, and will become more and more important in the future. In another project, we collaborated with the Department of Applied Physics at Aalto University, and in that project, the goal was to train a reinforcement learning agent to autonomously arrange atomic structures in real world with real equipment. So there is this scanning tunneling microscope tip, and we want to move atoms with that with this tip to a target location. And one solution would be to kind of script the policy for the tip, but this scripting is kind of difficult. And if the environment changes a little bit, then this agent may not behave in an optimal way. But instead, we train a reinforcement learning agent using the state-of-the-art soft critic algorithm, and that agent was able to move atoms in the real world with real equipment, and it was able to arrange atoms, for example, in this kind of structure. And this was published in Nature Communications last year. Okay, but now about the topic of today's lecture, it's about hierarchical imitation learning. So as I said, it's about how to improve planning in model-based reinforcement learning. So the motivation for hierarchical planning is that we want to build plans of how to act in an environment, but we want to create plans kind of on the high level. So we don't want to model sort of low-level actions. What kind of low-level action control commands I should use, but we want to kind of plan many steps ahead, and we want to plan to achieve some certain goals. And the hope is that if we are able to build such agent, that we can plan more efficiently and in more longer term, in longer scales. So, for example, if you want to play Minecraft, then there is a bunch of survival tips, like what you need to do in order to survive. For example, you need to locate trees, you need to start a house, and so on. And those are kind of easily understandable goals for us, but each of these goals requires a sequence of low-level actions, and we would like our agent to build these kind of representations that would be probably have some intuitive meaning for humans, but then they would also consist of multiple low-level actions, so kind of more high level planning. So this is related to hierarchical reinforcement learning. And in hierarchical reinforcement learning, you train an agent that has a hierarchy of like a hierarchical policy. You have, let's say, a manager policy that controls the low-level policies. So for example, it can pick one of the low-level policies to achieve certain, to do certain tasks. So typical environments is when like an agent is has to learn to move in an environment, and it has to control its so the actions are kind of low-level actions such as motor control commands. So some intuitive benefits of hierarchical RL is that you can kind of train and explore in a mostly manifold action space. So instead of like this low-level command, you have like high-level actions that makes more sense. That make more sense. Unfortunately, there is kind of evidence that the observed benefits of state-of-the-art hierarchical reinforcement learning can be attributed to improved exploration. For example, in this paper, they show that a non-hierarchical agent that was trained on experience collected by a hierarchical agent was able to achieve performance that is competitive to the performance of the hierarchical agent. So, which suggests that okay, hierarchical is important for exploration, but otherwise, is it really important? So in this work, we really want to focus on scenarios where the agent cannot do any exploration, and we want to find benefits from a hierarchical planning. That's why we consider an offline reinforcement learning scenario. So we assume that the agent cannot interact with the environment at training time. So it's just given a collection of demonstrations produced by an expert, and then the agent has to learn how to behave intelligently from those demonstrations only. And we hypothesize that in this kind of task, in the tasks that require careful planning, using a hierarchy for solving tasks can be very important, and that's why we consider this kind of complex tasks. So, for example, we consider four tasks. In the first task, this is a kind of a popular traveling salesman problem. The task is to visit all the cities that are marked with squares here, one by one. We start with the starting position that is marked with the black square, and then we need to visit all of these cities, and the visited cities are marked with the green squares, and then the unvisited cities are marked with red squares, and you need to visit all of them and return to the original position. Then we consider the sliding tile puzzle, which is a quite popular puzzle. You need to arrange the puzzles in order and by moving one puzzle at a time. Another environment is called box worlds. Here we have an agent that whose goal is to collect this gem marked here with the $sign. In order to collect this gem, the agent has to unlock a door, but in order to unlock the door, the agent has to have a key of the same color. So first it has to collect that key. So it has to open unlock another door to get this key, and in order to unlock that door, it needs to collect a key of that color. So it's a kind of task that requires planning and in order to succeed. And the fourth environment that we consider is called Sokoban. It's again a popular environment. The task here is to push yellow boxes onto predefined locations, target locations. And again here you need to do careful planning, and because if you do it if you push the boxes in the wrong order, then the puzzle may become unsolvable. So these are the environments that we consider, and those environments require planning, and we believe that there has to be some benefit from hierarchical planning. So in our setup, we assume that we have demonstrations produced by an expert which knows how to solve the task. So, for example, we have demonstrations by an expert who visits all the cities, and we have only demonstrations of the low-level commands, but we don't have any supervision on the high-level plan. So, for example, when the expert is moving from one city to another, we don't know to which city it's moving, but our hope is that our agent can figure out kind of the high-level plan of the expert in an unsupervised way. And the expert may not be optimal. For example, in a traveling salesman problem, the expert doesn't visit the cities in kind of an optimal order or close to the optimal order, but it visits the city in a random order. Okay, so how could we solve this task? So what would be the simplest solution to solve this problem? The simplest problem would be just to train a behavior cloning agent. So we just train an agent, a neural network that tries to maximize the probability of the action taken by the expert when the agent is in a given state ST. Another possibility that is quite popular at the moment is to train to do offline reinforcement learning, which means that we train a policy from the available data set collected by another potentially unknown policy, for the policy of our expert. For example, CQL is one of the popular algorithms of offline reinforcement learning. Okay, but does it work in this in our problems? You can see that we cannot really solve these problems with behavior cloning. If we just train a model to mimic what the expert is doing, then we cannot really learn to solve the puzzle. So here in this table, we show the success rate in solving the puzzles after training. So we're training a behavior cloning agent, and then we test it on new instances of the same environments. And then if we measure how often the agent is able to solve the environment, so to go from the starting position to the terminal position, which is kind of successful state. You can see that the offline RL algorithms don't really work well in these problems as well. So we propose another approach that we call a hierarchical imitation planner with search, or HIPS. And our approach consists of 3 steps, and those steps I will explain next. So the first step is learning representations of expert trajectories. So the idea is that we have a sequence of states that we observe in the expert's trajectory, and we represent each training trajectory as a sequence of subgoals, where each subgoal is one of the states that is observed along the trajectory. So instead of the original trajectory, we kind of learn key frames or key states that kind of summarize the whole trajectory. And the intuition is that each subgoal, so each intermediate state, should correspond to a meaningful high-level action, such as, for example, moving one box to a target location in Sokoban, or visiting a new city in traveling salesman problem, or moving one tile to a target location in a sliding tile path, and so on. So basically, this is a time series segmentation problem. So we want to segment our sequence of states into sort of sub trajectories, and we want to do it kind of in an intelligent way. Just to give you a spoiler, that if we just segment trajectories into intervals of fixed length k, for those environments, this the simple strategy actually works pretty well, and you can achieve quite good performance even with this strategy. But we believe that there has to be a more reasonable way of subgoal identification, a more reasonable way of splitting, like of the trajectory segmentation and kind of subgoal identification. But it turned out that it's a very hard problem, and we tried many things, and one solution really worked, and we kind of explain what the solution is. So the intuition behind our approach is that the subgoals that we want to find should preferably be as far as possible from each other, from the current state. So if they are kind of far away from each other, then we could do faster planning. We can kind of move faster from one state to another, and we can move faster to the end state. On the other hand, the agent, the low-level agent, like a simple agent, simple behavior cloning agent, should know how to reach a specified subgoal. So if we are in this particular state and we give the next subgoal as the target to our simple behavior cloning agent, then it needs to know how to actually reach that state. And the third requirement that we have is that the subgoals should be possible to generate, because we want to later, when we kind of train a generative model of subgoals, we want to do planning in terms of subgoals instead of planning in terms of low-level action. So our subgoals have to be such that we could generate those. So our approach is to formulate this problem as a reinforcement learning problem. And in this problem, we consider we treat one trajectory provided by the expert as one episode of training of our so-called segmenter agent, the agent that performs segmentation. And the segmenter agent starts with the starting position as 0, and it selects one of the future states as the next subgoal according to its policy. And we consider only the following age states just to make it a tractable problem. And then once it selects the next subgoal, the segmenter agent moves, so changes its state to the new subgoal state, and then it gets the reward. And the reward is written over here. It's the sum of the log probabilities of the sequence of actions observed in the expert trajectory between the initial state 0 and the first subgoal, produced by a behavior cloning agent that we concurrently train in the segmentation process. So we train a behavior cloning agent, and the reward is high if this behavior cloning agent can actually reproduce the behavior of the expert in the subtrajectory. Then we add some penalty alpha, and this penalty encourages kind of longer subtrajectories, because every time you decide to make a stop in a particular state, you have to pay a penalty of alpha, so that you are encouraged to make as a long step as possible. So the segmentation continues in the same way until we reach the final state. So this is kind of one episode of training. And the segmentation agent is trained using policy gradient algorithm reinforce. And the low-level policy that is used to formulate the reward for the segmenter agent is considered as part of the environment, and we train it concurrently. And it's basically trained as by minimizing this loss, basically a goal condition behavior cloning agent. Okay, do you have any questions about this first step? Any questions?
Could you perhaps repeat a little bit on the extracting the subgoals? Was sort of this how do you sort of conclude what's going to be the subgoal?
Yeah, so this is the reward that the segmenter agent receives.
Oh, right, so, it's for the segmenter.
Yeah, so the segmenter receives high reward if the low-level behavior cloning agent knows how to repeat the trajectory from point A to point B, or in this case, from this red state to this state marked with black, and also some penalty for making a stop. So it would be nice if you would kind of select as the next subgoal the state that is as far as possible. So we penalize every stop that the segmenter agent does. But then we also kind of reward the agent if the state is reachable by the low-level policy. And we just, this is kind of the intuition behind this.
Great, thank you. There's a question in the chat. Are the results sensitive to the penalty alpha?
Of course, there is some sensitivity to that, but it's not very bad. Of course, like if you set alpha to be too big, then it may change the result significantly. But if you very alpha in a kind of reasonable range, there's not much effects on the results.
Great.
Okay, so this was the first step. And in the second step, so the idea that we want to do next, we want to do planning, perform planning in terms of those sub-goals, high-level goals. And in order to do that, we need to create a generative model of sub-goals. So the task of the generative model is that, given the current state of the environment, generate possible sub-goals that could be useful for planning. So, and those sub-goals should probably be such that were observed in the expert trajectories, and those were probably the sub-goals that were identified in the first step. So we train a generative model of the sub-goals given the current state. And we use the data that we produced in the first segmentation step as the training data. And as the generative model, we use a variation autoencoder with discrete latent codes, VQVA, and it's largely inspired by this paper from ICML 2021. And the model consists of the encoder and a decoder. The encoder takes as inputs a pair of states, the current state and the next sub-goal, and it generates first a continuous latent code, Z, which is then quantized. So it's converted, let's say, to a nearest code from the code book. And the decoder takes that code, that quantized code, and also the current state, and produces the next sub-goal. So you can see that our autoencoder, it doesn't encode the current state. No, it encodes the next sub-goal, but it rather encodes the difference between the current state and the sub-goal. So it's kind of a what should you do on the high level to go from the current state to the next sub-goal. So given this kind of code that is kind of the plan or the high-level action that we produce by the encoder, we know how to move from the current state, how to change the current state to obtain the next sub-goal. And once this VQV is trained, we can use the decoder of this model to generate reasonable sub-goals for the current state. So the way it works is that we generate those codes according to some prior that we also learn for the VQVA, and we use those codes as the input of the decoder, and they will also use the current state as the input of the decoder, and we produce the next goals. And so because we have a finite number of possible codes here in the kind of latent space, we can produce also only a final number of sub-goals given if for any state. And for some subcodes, it may happen that different codes correspond to the same subgoal. So let's say sample different codes, but they all correspond to the same subgoal. And we think that it's a kind of a nice behavior because in some situations, for example, when you are very close to the terminal states to solving the puzzle, there are not that many options. There are not that reasonable, that many reasonable subgoals that you need to generate, and kind of we don't have any direct control over this how many subgoals we need, but the model learns itself. So sometimes it just learns that several codes correspond to the same subgoals. And all of these networks are resonance-based CNNs, and the decoder also has film layers in order to process the latent code. Do you have questions about the second step? Is that clear? Do you understand the reason why we are doing this and how we are doing this? Okay, so let's move on to the next step, and maybe it will become more clear, and we can discuss after that. So in the third step, we use the generative model that we produced in the second step in order to perform planning in the subgoal space. So instead of doing search in the state space using low-level actions, we perform search in the subgoal space using high-level actions, where those high-level actions corresponds to those codes that we use as the input of the VQVA decoder. So the way it works is that we start with the initial state, and we use that state to generate possible subgoals using our VQVA model. So we just basically sample different codes and produce different subgoals. And then we select the next most promising node from the currently available states in this tree, and we do expansion of that node. And we sort of proceed until we find a node that corresponds to the terminal state. And so just a few notes here. One note is that we try to avoid duplicate states. So if we already have the same state in our search queue, then we don't add another state, identical state. And another note is that when we generate a state with our VQVA, we first check whether the state is reachable from the current state, because sometimes the model is not perfect, so sometimes it generates states that cannot be reached. And in order to verify if the state is reachable or not, we perform several steps of we run several steps of the lower level policy, starting from the current state and trying to achieve that goal that we test. And if the goal is reached within a certain number of steps, then we assume that the subgoal is reachable, and then we add it to the search queue. And so we have two differences, like when we do this reachability analysis, we can use either the known environment dynamics, in which case we assume that we know the low-level dynamics of the environment, or we can just train a low-level dynamics using a neural network, and we use a learned model of the environment in order to check the the reachability. And we use several search algorithms, and the search algorithms are different in how you prioritize different nodes for expansion. So there's this greedy best first search, policy guided heuristic search, A-star or Monte Carlo tree search, kind of standard off the shelf search algorithms from the literature. So just how it looks in code, it's kind of very simple. You have a queue, priority queue, you create a node that corresponds to the starting, like the initial position of the environment, then you insert it to the queue, and then you take the node from that queue that has the highest priority. So if we have only one node, that would be that node. Then we do the expansion, perform the expansion, and this is done with our VQVA model. And then for each node that we just created, we check whether it's a terminal state or not. If it's a terminal state, we just exit and assume that we found the solution. If it's not a terminal state, we compute the priority of that node using different heuristics, and the heuristics depend on what kind of algorithm you use, and then just insert those children nodes to the priority queues, and then we just iterate this. And if we have gone through all the nodes and we didn't find the terminal, we didn't reach the terminal state, that we assume that the search failed. Do you have any questions about this part?
Yeah, can I ask a question?
Yes, sure.
Yeah, yes, sure. So that means you started from the trajectory. That means it's like if I summarize this whole thing so that I can make clear picture. then you identify the key goals, and then from those key goals, you have generative models that can generate sub-goals. And then that means like for your search space, for example, your how to say sample state space of this reinforcement learning consists of those key goals, and from that key goal, so that you can generate the sub goals, like you can interpolate the intermediate states of this trajectory. Is it like that? If I make
So there is no difference between key goals, key states or sub goals. So the key states are the sub goals, right?
Key, yeah.
So we just segment the trajectory into into sub goals, like key states, and then we build a generative model that if you are in this state, our generative model should be able to produce, for example, this state. Or if you are in this model, then our generative model should be able to produce this state. From this state, it should be able to produce this state.
This state, okay, yeah. Okay. So it learn from this that what are the key? What are the sub goals in that? So it's like hierarchy, but this hierarchy, but the state space in our reinforcement learning are those key goals. Is it like that?
The states are what?
The policy, I mean, in the reinforcement learning, the sample space of these goals are actually just like finite state space. Is it like this?
Yeah. So first of all, so the sub goals live in in the observation space. So,
okay.
And second is that we have a probabilistic model with with a finite number of possibilities for every state. So if we're in this state, we can generate only k possible sub goals, and one of them should be, for example, this one. So we train the model such that it can generate those sub goals that we have seen after the segmentation process.
Perfect. Got it. Thank you.
Okay. Any other questions? Okay, so the experimental results, we have considered those 4 environments. And so first I want to visualize what kind of sub-goals our VQ-VAE is able to generate. In this example, we are in a certain state. So for example, this is the state of the environment. And these are the sub-goals generated by our generative model. And as you can see, in the current state, we are visiting this city, but our generative model suggests visiting one of the unvisited cities as the next possible sub-goal, which intuitively makes sense because this is how we kind of solve the traveling salesman problem. So it learned to identify visiting the next city, one of the unvisited cities as one of the possible future sub-goals. In other environments, such as Sokobban, you cannot really find a very good interpretation of what sub-goals are, what the sub-goals are. For example, in this example, we are in this state, and these are the sub-goals generated by our model. And basically, my interpretation is that we consider moving our agent to one of the available empty cells, and we can move one or no boxes on the way. So in this case, for example, we moved this box here, but I guess in the other sub-goals, the agent was just moved to one of the empty cells without moving any boxes. And this is an example of a high-level plan found by our search agent. So by generating those sub-goals, we can now optimize our trajectory and kind of plan the whole trajectory in terms of the sub-goals. So this is one of the trajectories that we found in the search procedure. You can see that we start from the initial position, and then we just visit all the cities. In this particular example, we also asked our agent to minimize the number of steps. So we wanted to visit the cities in the minimum possible number of steps, and you can see that it finds a solution that looks very reasonable. This is just an example of a high-level plan produced for Sokoban. So, for example, here it decides to move one box, this box over here. In this subgoal, it just pushes this box downwards. Next, it decides to push this box to this location. Then it decides to push the box, this box further. Then it decides to push these boxes to these positions. And now it's a simple task, so it knows how to do to push those boxes. And then finally, it's in this state, and it knows how to push this box to this position and this box to this position. So this is kind of a high-level plan that our agent was able to generate. This is an example of a sliding tile puzzle, but basically the plan also makes sense. It just the agent tries to move the puzzles one by one to the target locations. Okay, but is it able to solve the task? And in this table, we can see the solution rates for solving the puzzles, and you can see that our agent is able actually to solve quite a large portion of those puzzles. So it works much better than the simple behavior cloning policy. It doesn't do very well on the box world environment, but the problem here is that the low-level dynamics of the environment was not learned correctly, because in the training demonstrations produced by the expert, there were very few transitions of opening a colored door with a wrong colored key, and so the agent was just not able to plan those, like to test the reachability of subgoals correctly. And once we replace this low-level policy with the simulator, we can actually see that the high-level planning works well, but it's just that the problem is in the low-level dynamics model. When we were doing this work, we actually also found a paper that was from years 2021 that was doing a similar thing. They used different subgoal generation model, and they also did segmentation of the trajectories into a fixed length interval of size k, but we were able to outperform those that algorithm by a good margin. So in the next table, I want to show that that we can find a solution using our high-level planning faster compared to let's say other like baseline methods. So here we report the success rates after performing n node expansion. So we test we consider n trees in our search queue, and what is the chance that we actually solve the whole puzzle after inserting only n nodes to our search queue. And you can see that our algorithm performs better compared to this baseline, and also we have a low-level search algorithm PHS, which operates with low-level actions, and you can see that it's much more efficient to do search on high level rather than doing search on the low level. Then one thing that was surprising was that if we don't do any intelligent segmentation, but if we just split our trajectories into sub-trajectories of fixed lengths of length k, but otherwise we use the same generative model and the same algorithm, then this actually works pretty well in those environments. But still having this more intelligent generative model, so the model that can generate sub-trajectories of varying lengths, is beneficial because you can find the right solution using a few node expansions. So it can make larger steps. And by the way, this K was tuned so we kind of had to tune K to get these numbers, because this algorithm is sensitive, of course, very much sensitive to the value of K that you select. Okay, so in the last slide about the experimental results, I want to show that our agent can actually outperform, even it has the potential to outperform the expert that whose data it used to train the model. In this table, we show the average number of steps that our agent did in order to visit all the cities in the traveling salesman problem. And so the expert demonstrations, the teacher visited cities in a random order, and on the average, it used 336 steps, environment steps, to visit all the cities. But if we use our algorithm and our planning algorithm in the high level, in the subgoal subspace, and if we want to minimize the number of steps taken in the environment to visit all the cities, we can actually perform much better compared to the agent. So the idea is that our agent looks at the behavior of the expert. It tries to understand what could be the high-level goals that the expert has in this at different points of time, and that it builds a generative model that tries to generate those goals. And if you want to optimize a certain metric, for example, the number of environment steps that the agent needs to take to visit all the cities in this example, then we can actually search in the space of the experts, kind of expert-like subgoals, and we can even improve the performance compared to the performance of the expert. So this work is just a baby step towards learning abstract representations of experiences. So I think it would be very important in the future to build representations of experiences, to kind of build representations of what the agent has seen so far, so that or what the agent has done, let's say, in the previous n steps, so that it can kind of learn, it can plan its actions using this kind of abstract representation, so kind of high-level controls or high-level actions. So, of course, there's a lot of potential for future research. For example, we can combine high-level search and low-level search, because if our generative model of subgoals is not perfect, then there's no guarantee that we can actually find a solution. And but if we do low-level search, we can actually guarantee that. So if we combine those two, we can have a compromise, so we can plan faster, but also have some convergence guarantees from the low-level planning. Of course, it would be very nice to learn hierarchical representations from high-dimensional inputs, such as images, and also extend it to continuous actions. Another limitation of this work is that we formulate goals in the observation space, and this is not optimal because for many reasons. One reason could be that the observations can have a lot of irrelevant observations, destructors. So when we formulate the goal, it might be better to formulate this goal kind of in the abstract space rather than in the observation space. And another direction that I want to kind of mention here is that it would be interesting to kind of correlate those abstract representations of high-level actions or high-level goals with language instructions. So, for example, if we are in a certain environment and we are given an instruction in natural language, it would be nice to kind of understand the meaning of each part of the language instruction in terms of this kind of high-level goals or high-level commands that the agent needs to do. So that was the last slide of my presentation. Do you have any questions?
Thank you, Alexander. I think I have sort of a question. Thinking about the subgoals and how you extract them and how you could. I mean, you have demonstrated this for some tasks. What if you have more complicated tasks or more real world tasks? How simple do the subgoals have to be?
So in this work, we kind of tested these three principles for the subgoal generation. So the subgoals should preferably be as far as possible, and they should be reachable and should be possible to generate, because we need to be able to plan in terms of the subgoals. But if we go to more complex tasks, let's say you have an agent that receives sensory inputs as kind of videos, then I believe that we could still probably use the same intuitions and the same principles, but we would probably have to do it in the latent space rather than in the observation space in order to do the same thing. Yeah, that's my understanding, at least.
Sounds reasonable. Do we have some more questions from the attendees? Well, otherwise, thank you very much, Alexander, for this interesting talk. The next seminar is in 2 weeks, so it's March 9th. We'll have Shay Cohen from University of Edinburgh speaking about document summarization, so natural language processing.
Thank you very much.
Thank you.
Bye-bye.